Hey guys, we're in the last lesson, section 5. We're looking at exponential, logistic, and logarithmic modeling today, putting some real-life applications to our lesson on logarithms and exponential functions. Here in example 1, we're going to look at a logistics model, and we see that the function f of t is given by this expression, and it describes a number of people who have become ill with the flu outbreak T weeks after its initial discovery in a town that had a population of 64,000 people. So we want to know how many people were ill at the beginning of the epidemic. So this sounds kind of familiar, doesn't it, in 2020? If we just substitute 0 in place of the time, you have 1 plus 4,500 e to the 0 power, and e to the 0 power is 1, so that becomes 64,000 divided by 4,500, 1 people. So using our calculator, we have 64,000 divided by 4,501, and that's roughly 14 people. So the f of 0 is about 14 people initially are sick in the town that has 64,000 people. That's at the beginning of the epidemic. How many people were ill at the end of the 4th week? Well, that would require substituting 4 into the formula, 64,000, and 1 plus 4,500 e to the negative 12 times 4. So that's going to be to the negative 48 power. So we can calculate that here. Whoop, not there. 64,000 and 1 plus 4,500 e to the negative 12 times 4, or negative 48 power. Let's put a decimal in there. And what happened to that? Something went wrong. That shouldn't work like that. Okay, I see what my mistake is. I'm supposed to have a decimal in there, right there. I missed that here. So let's give that a try again with the calculator. So I've graphed it on the calculator, and we can ask for, the function value on that graph at 4 weeks. That's more like it, 1,682.71 people. So roughly we're going to round down, because 0.72 people, that's not a whole person. So at the end of the 4th week, there are 1,682 people that have become infected with that flu. And then part C, what would be the limiting size of the function f of t? The population that can become ill? Well, that would be the maximum population for 64,000 people, because that would be the carrying capacity of the entire population. That's called the limiting factor. The limiting factor. So that graph would look something along the lines of some curvy graph, and it would be asymptotic at 64,000 people. In examples 2 through 4, we're going to use the population growth model right here. So example 2, we want to determine the exponential function that's increasing at a rate of 6%. So in that increase, we need to add 6% to the population formula. So I want 12 times 1 plus 6%, and 6% has to be written as a decimal to the t power. So the population would be 12 times 1.06 to the t power, since p sub 0 is this initial amount right here. So this is our function that would relate that statement to algebraic terms. Example 3, suppose that we have a culture with 100 bacteria. It's put in a petri dish and the culture doubles every hour. So doubles every hour is our base. Predict when the number of bacteria will be 250,000. So the population model would be our initial is 100, p sub 0 is 100, and then the rate would be doubling every hour, so 2 to the t power. We want to know when there's going to be 250,000 bacteria, and we could figure this by dividing out by 100. So 100 leaves us 2,500, 2 to the t. So if we want to solve for t, we need to take the natural log of the left and the natural log of the right, and then use the properties of logarithms. So t comes downstairs, and we're looking at natural log of 2,500 divided by the natural log of 2. Now on our calculator, let's pull that back up. We've got in the numerator natural log of 2,500 divided by, in the denominator, natural log of 2. So it's going to take 11.287 hours. So 11.287 hours. Now, I'll let you do this. I'm going to show you what I would do if I wanted to solve graphically. I'm going to draw on my calculator the function 100 times 2 to the x power. So that's going to look something like this. This is my function. Y equals 100 times 2 to the x power. So we're calling that y1. And we know the answer is out here somewhere. So I'm going to go at least out to 15, because I know the answer algebraically is 11. And then we want to make the window really large, so maybe go 300,000 up here. So this line, y2, is going to be 250,000. And you can zoom way out if you want. But it's that intersection point, that xy value, should read 11.287 and 250,000. So when x is 11 hours, y is 250,000. That's our intersection point. That's where the two graphs intersect. So we're using that approach where this one is your y2 graph, the 250, and this curvy one is our y1 graph, the population model. This one's y1. And then this side here is y2. Okay? So just using a calculator to solve what we already knew algebraically. Then the last one with that model, we want to suppose that the half-life of a certain radioactive substance is 40 days. There's 8 grams initially, and we want to know when there's just going to be 1 gram remaining. So the population at time 0 is 8. The base, they want us to use 1 plus r, and we're told it's a decay. And what's happening? In 40 days, find the rate of decay. So 1 minus a half, the half-life would be, the base would be a half. So our population model would be the p sub 0 times half-life, and then I'm going to work this one, the t divided by 40. This is a way that we see in Algebra 2 often. So t over 40 is going to represent the number of half-lives. So that's my power. So on my calculator, calculator, we want to put y1 in the calculator, 8 times 0.5 to the x divided by 40 power, and then y2 is what we want to have remaining, that's 1. So let's go try that one out. That'll be a small window. We can do that one pretty quickly on the calculator. So 8 times the half power raised to x is y1, and then in y2 we want 1 remaining gram, so move these out of the way, and where they intersect right there is what we're looking for. That's going to be our solution. So the intersection is going to come at, oh, that didn't work out right. Oh, I put my power wrong, didn't I? Back that bus up. Let's go back there. It's x divided by 40. X divided by 40. And y equals 1. So we want to go way out there. Let's say we go out, I don't know, 180 units. This is in what, days? In days. Okay, so there's our intersection. Menu, analyze, intersection. So that makes sense. So 120 days, we'll have 1 gram remaining. That's at that intersection. So you might want to draw a picture for yourself here, just to leave a little record in your notes. So you've got, this is your y1 graph, and this is your y2 graph. This is y2 equals 1, and this is your y1 is your population equation. And they intersected at 120 days, 1 gram remains. So that's the intersection point. We've got 1 gram remaining at 120 days. So we're modeling with the population growth and decay model and logistics functions. Here's another equation, uninhibited growth of cells formula, often seen this way, using E as our base. Instead of the 1 plus the rate, we've got continuous exponential growth or decay. So if the K is negative, that would be decay. If K is positive, that would be growth. In example 5, a culture of bacteria follows the law of uninhibited growth. And we have 500 bacteria initially. That's our A sub 0. So 0, 500 tells me that A sub naught is 500. And 1 hour later, there are 800 bacteria present. So we want to first write an equation that would model this behavior. So we got 500 is A sub naught, e to the kt power, and we're going to use this point here. After 1 hour, there's 800 bacteria remaining. So 800 divided by 500 is e to the k power. If we take the natural log of the left and the natural log of the right, the k is all alone. This is our constant, or our rate. Now, if you calculate that with the calculator, you're going to find out it's about 0.4700. But this is sufficient too. So using that information, we're going to take this formula here, and we're going to solve the A of t. This is going to be our formula now, is 500 e to the natural log of 8/5 or 0.47 t power. So you can put whichever, either this one or this one up here in your K location, right? And they want us to calculate 5 hours later. So we would use our calculator and do 0.47 times 5. I'll wait on you. I got 5,242 bacteria are now in our collection from that initial 500 bacteria in just 5 hours. So now, how long before the culture contains 20,000 bacteria? So we've got our model. That was A of t is 500 e to the 0.47 t power. And we want to know, we're going to solve for time this time. So we've got 20,000 bacteria where we had 500 initially. And we want to find out how much time passes to get that 20,000. So we're going to divide by 500. That's going to leave 40. E to the 0.47 t. So take the natural log of 40 and the natural log of e to the 0.47 t. Natural log of e is 1. So the time would be natural log of 40 divided by 0.47. So let's go figure that out. Clear this off. And we've got the natural log of 40 divided by 0.47. And that's 7.848 hours. So 7.848 hours before there will be 20,000 bacteria in that growth. Now, if you wanted to figure out how many minutes 0.848 is, you could say 0.848, that's 100%. So x is to 60 minutes as 0.848 is to 100. So this divided by 100 leaves us about 51 minutes. So if you needed to, you could convert that and say 7 hours and 51 minutes. At about that time, there will be 20,000 bacteria present in that growth. And then our last couple of examples, they're about regression. Well, one of them's regression and one of them is another logistics. So here we want to go put these values into our calculator. Had a little bit of trouble with that the other day. So up here we're putting X for our weeks. And we've got 0, 1, 2, 3, 4, 5, 6. And make sure I go back to the top again. And Y. So we don't want to start on row 4. We want to start on row 1. So we got 100. 90.4, 76 point, whoop, missed that, 76.8. The third week is 69 7/10, then 58 2/10, 49.7, and the last week 44.2. So let's make sure we did them all right this time, since I messed it up the last time. That looks pretty good. Okay, so we're going to control, insert the data and line up the X's on the X-axis and then line up the Y's on the Y-axis. And we're looking for an exponential regression. So they're asking us to do an exponential regression of the radioactive decay. So this one we've got 102.306. I need to write that one down. I have a different one on my calculator. 102.306 times 0.8693 to the x power. Okay. So this calculator gave us the model 102.306 times 0.8693 to the x. And we want to know, using that model, on part B, what's the half-life? So half-life, we would start off with 100 and end up with 50. So 102.306, 8693 to the x. This is my initial, so that makes me wonder about my numbers. Make sure I got those in there correctly. 100, 90.4, 76.8, 69.7, 58.2, 49.7. Okay. So my TI-84 gave me closer to the actual 100. But we'll work it this way. So 50, we're going to divide both sides by 102. So let's get out of there. 50 divided by 102.306 leaves us with 0.48873. Okay, 0.48873 is 0.8693 to the x. So taking natural log of both sides, 48873, and natural log of the 8693 will bring the x power down, and then we would divide 8693. So back to the calculator, dividing by natural log 0.48873, and then the denominator, natural log 0.8693. We got 5.11. Excuse me. So we got 5.11 weeks for that. And when will there be 10 grams left? So we want to take 10 in our formula, 102.306.8693 to the x power, and 10 divided by 102.306. So we got 10 divided by 102.306 is 0.0977. Okay, so we got natural log of 0.977 divided by natural log 8693. So that should be about 17 weeks or something. So natural log 0.0977 divided by natural log 0.8693. 16.6 weeks. So I was close. 16.6, what was it? 605. 16.605 weeks. And then part D, how much radioactive material would be left after 52 weeks? So we have our formula. Y is 102.306 times 0.8693 to 52 weeks. So looking at that, we got 102.306 times 0.8693 to the 52nd power for the week. So we got 0.0702. of a gram, not even a whole gram left. Now my TI-84 gave me a different answer all the way through. On part A, on the TI-84, I got 100.367 times 879 to the x. On part B, my answer was about 5.4 weeks. And part C, my answer was about 17.88 weeks. And then on part D, I had 0.123 of a gram that remained. So depending on which calculator you use, you could arrive at similar, close, but different answers. Then here's our last example. Surfside High has 1,500 students. Max, Patty, Juan, and Andrea start a rumor, and it spreads logistically so that this is the formula that models the number of students who heard the rumor by the end of T days, and 0 is the day the rumor begins. So we want to know initially how many students heard the rumor by the end of that 0 day. So that would be 38e to the negative 0.9 times 0. So that's 1,500. And we've got 1 plus 38, so we're dividing by 39. And you can check my work to be sure. I got about 38 students had heard the rumor by the end of that first day in a population of 1,500 kids. So how long does it take before 1,000 students hear the rumor? We can do that with this model, solving S of x in our calculator, and then the second equation would be 1,000 students. So let's go look at that on our calculator. So here's what's going to happen. We want to know if that's 38 and we go up here, there's 1,500 students is our limiting factor. Can't go past 1,500. And we want to know back here at 1,000, where do they intersect? So how many days, this is the time here, how many days before 1,000 students hear that rumor? So looking at our calculator again, we're going to put that first function, which is 1,500 in the numerator. Uh-oh, that didn't go so well. 1,500 in the numerator. Well, that's still not going very well. 1500. And then 1, nope, it won't let me do that. 1 plus 38 e to the negative 0.9 x power. So we got that function. And then we're going to put y2 is going to be 1,000. And we want to set the window to be, go out about 20 days. How about that? 20 days. And we'll go up to like 1,500 kids because that's the maximum it can be. 1500. Okay, so we're looking for that intersection. Here's our population model. Here's our goal. And we want to analyze for the intersection. So at the end of the 5th day, 4.81 days. So by the end of the 5th day, because this was 4.81 when y was 1,000, that was our intersection point, 1,000 students have heard the rumor. And we are finished with Unit 3.